Today, we're going to discuss divergent series, and several reasons for this. So the first is one I've alluded to several times already, which is that perturbation series in physics are generally asymptotic and divergent. So a natural question to ask is, well, if the best we can do is to find a divergent series approximation to the quantity we're interested in, how do we go back and recover information about the quantity we're interested in if the series diverges? So clearly, the series contains some information about it because, well, this is the best we can do in most cases, is calculate a divergent series, and theory matches experiments, but there's some disconnect there because the series, based on what we've seen so far, the series we generally construct, for example, using the saddle point method, are divergent asymptotic series. So we'll see. I'll say a little bit about how to interpret those results and what information we can recover from a divergent asymptotic series about some finite quantity of interest. So that's a very general phenomenon in physics. We generally can't construct convergent series. But in quantum field theory in particular, divergent series sometimes just occur on their own. For example, in quantum field theory 1, we're going to study the Casimir effect, which is basically causes a force between two parallel neutral plates in vacuum. So one way to derive the Casimir force is by directly by writing down a divergent series and using some of the techniques we'll talk about in lecture today, we can sum, in a sense, that series and derive the finite Casimir force. And divergent series like this, as well as divergent integrals, which in a sense are very close to a divergent series. Instead of summing a discrete set of terms, you're summing a continuous set of terms, but conceptually, divergent integrals, which occur all over the place in quantum field theory, are very similar to divergent series. And in the quantum field theory course, we'll talk about many ways in which we can assign a finite value to a divergent integral. I won't, in today's lecture, I won't discuss divergent integrals, but there's a very close connection between divergent series and divergent integrals that we'll see more about how to interpret divergent integrals in the quantum field theory courses later in the year. So that's some of the reasons why we're interested in divergent series. And let me just give you a few examples of what I mean by a divergent series. So the first one example, famous example of a divergent series is this series, whose terms are alternating plus and minus 1. This series is known as Grandi's series, after Guido Grandi was the first one to study this. So why is this a divergent series?
It's not absolutely convergent, like you take the absolute down.
That's right. So it's not so by a divergent series, I mean any series that's not convergent. So this series doesn't converge because its partial sums oscillate between 1 and 0. So it doesn't converge, therefore it's divergent. Another example So this is oscillating partial sums. Therefore, it does not converge. And that means it's divergent. By divergence, divergent series doesn't mean the partial sums necessarily diverge, just means they don't converge. The second example is this series. So I was unable to determine who was the first person to study this series, so I'll just call it someone series. With this series, the partial sums do diverge. So this is maybe what the first type of series you'll think about when you think about a divergent series, but I'm including both types, ones where the partial sums diverge or where they oscillate or simply don't converge. Another example is this series. Now, all I've done is taken Grandy's series and added a 0 in between the positive and negative 1. You might think there's a close relation between these two, but as we'll see in a moment, we need to be careful. The rules of addition are, when we're dealing with divergent series work, you have to be careful applying the rules of addition. They might not work the way you expect compared to your experience working with finite sums. So these two series are different, even though all I've done is added 0 to a Grandy series. And you could write down a bunch of other examples of divergent series. Okay, so what are the properties of addition when that we need to keep in mind when we're dealing with divergent series? So one of the key properties of addition that you're all used to using is associativity. So let's assume addition is associative. In that case, Grandy's series I can put in parentheses wherever I like, assuming addition is associative. And Grandy's series can be written as 0 plus 0 plus 0, which is a convergent series, which adds up to 0. So if addition is associative, Grandy's series must be equal to 0. If it's associative, though, I can also put in parentheses in between the second and third term and the fourth and fifth term, in which case Grandy's series is 1 plus 0 plus 0 and so on, and therefore Grandy's series sums to 1. So if I assume addition is associative, I get a contradiction. Therefore, conclude that addition is not associative, or more precisely, it's not infinitely associative. We're only allowed to use associativity finitely many times. It's not infinitely associative. So if we're going to have any chance of assigning in a consistent way a finite value to a divergent series, we can't use it associativity infinitely many times. Okay, so addition is not associative. What about commutative? So if we assume addition is commutative, then what we can do is we can take a convergent series, a conditionally convergent series, like the series for the log of 2, which can be written as 1 minus a half plus a third minus a quarter, and so on. So this is a convergent series. It converges to the log of 2. It's a conditionally convergent series. It has divergent subseries. So this series converges, but 1 plus a third plus a fifth, and minus a half minus a quarter minus a sixth are divergent series. So it contains divergent subseries, or it's a conditionally convergent series. So let's assume addition is commutative. In that case, if I'm allowed to commute things, I can make this series add up to anything I like. And then again, we'll derive a contradiction. So for example, suppose I want to use commute the terms in the series to make the series add up to pi. I can do that as follows. So I can construct a series whose terms are exactly the terms in this convergent series for the log of 2 that adds up to pi just by first having including terms, positive terms, until I get enough terms so that the partial sum is greater than pi. And then I can add negative terms, starting from the largest negative terms, until the partial sum is less than pi, and so on. I can then add some positive terms. So the partial sum is greater than pi, negative terms, so we go less than pi. And where I start here with the first term I didn't use, first positive term I didn't use over here, I'll overshoot each time. So first I overshoot by pi, but the amount I overshoot will eventually decrease because I'm adding smaller and smaller terms. So the most I could possibly overshoot for in this term is, suppose this term stops at 1 over 2n plus 1. This term could at most overshoot by 1 over 2n plus 3. And as I go farther and farther, I'm overshooting by, at most, a smaller and smaller number. So this, you can construct a series like this, whose terms are exactly the same terms as those in the series, convergent series for log 2. This series converges to pi. And I could pick any other number I like here. So conclude, again, that addition is not commutative. So addition is not associative or commutative. So these are two things we're not allowed to do when we're working with divergent series. Okay. So nevertheless, even though our most familiar properties of addition don't hold when we're working with divergent series, it is possible to assign a finite number to divergent series like these. So first, I'll show you that it's possible, and then I'll try to convince you that there's some meaning behind these procedures. So one way in which we can assign a finite number to a divergent series is known as Euler summation. And so let's suppose we have some divergent series, which I'll call phi. It's the sum of some terms an. So if this diverges, is a divergent series, and the an grow slowly enough, say an goes like n to the k, some fixed k, then f of x is the sum of an x to the n converges for x less than 1. So if these grow at most like n to the k, then x to the n for n large enough will eventually go to 0 faster than these go to infinity. So this sum will then converge. And so this is a way in which we can make a divergent series converge. It only works for certain series. And the Euler sum is defined to be the limit as x approaches 1 from below of f of x. This is called the Euler sum. So this is a procedure we can use to assign a finite number to a divergent series. Okay, so I'm going to give you a few minutes to work out what the Euler sum of Grandy's series. So you can see that this is a procedure we can use to assign a finite number to a divergent series. This one here is Grandy's series. As usual, feel free to discuss each other. you're finished, just thumbs up. Okay, two more minutes. Okay. Somebody walk me through their solution.
So the point is to notice that if you put an x in front of the series, then you can take the first term and for the rest of the terms factor an x and you will get your series back. And then you can manipulate that algebraically to give the sum, which is a half.
Okay. So your claim is that f of x was equal to your claim was that f of x is equal to x times.
My claim is that f of x equals 1 plus x times f of x.
Okay. F of x is 1 plus
1 minus x times
f of x. By pulling out the term and factoring out, and then we can get f of x is 1 over 1 plus x. Yes, I agree with that.
X minus x times f of x, right?
X. No, I get that.
Well, there's x minus x times f of x. Yeah, x times quantity 1 minus x.
So if we solve this, we get 1 over. I agree with this. We can also.
You have to make sure that n goes from 0. That's probably what's wrong. So the first term in the series has to be a 1.
Oh, I see.
It's 1 minus x plus x squared minus x cubed.
Another way to see it is that this is just a geometric series, so it can directly sum the. If you remember the formula for a geometric series, the sum is that. So then plugging in x equals 1, we get the Euler sum. Okay. So we have assigned a finite number to a geometric series, to a divergent series. And, well, so it may seem rather arbitrary to you. There's lots of other ways we could have tried to assign a finite number to a divergent series. One thing to note is that the partial sums of Grandi's series alternate between 0 and a half, 0 and 1. So the average partial sum is a half. So this is perhaps not an unreasonable number to get. So it's not unreasonable, but may seem arbitrary. So let's try another procedure and see what we get.
I see how the Euler summation is something special because all you're doing, you just said, that is just geometric series if you,
Right.
like when you do geometric series, you never care about the constant in front of your x, like the comma ratio. So like I'm not seeing what is something new about the Euler summation in comparison to, hey, this is just a geometric series, let's determine when it can converge or not.
Well, so what we've done, Euler summation assigns number half, which is a finite number, to this divergent series. Grandi's series does not converge. If we just, so the usual way we would define the limit of a series would be the limit of the partial sums. That doesn't converge. It just oscillates between 0 and 1. So using the usual definition of the sum of a series, we can't get an answer.
But you're using that geometric series, the f, to construct that.
That's right.
It's like I feel like, well, it's not that series itself that I'm studying. I'm studying a geometric series, and I take a particular limit of it.
That's right.
Like I feel it's like.
Well, this is only geometric. Well, depending on what the ANs are, this happens to be a geometric series. But we could have, for example, we could write down other divergent series. AN could be n, for example.
Okay.
That would be another divergent series that we could sum this way, or it wouldn't be a geometric series.
And what really relates to the series is that what we eventually want is that the summation machine actually isn't, like, is the one that we use to get the result, but the result is independent of the summation machine. I mean, that will eventually happen for some summation machines, right? That they will give results independent, like based on certain axioms, right?
That's right. So this may seem arbitrary, that this is a point we're going to come back to. So I'm going to argue that it's not as arbitrary as it seems so far. Okay, so there's another possible way that we can assign a finite number to a divergent series. And the idea behind this method is based on the observation that n factorial, or gamma of n plus 1, can be written as e to the minus t of t to the n. And so 1 is equal to the integral from 0 to infinity, dt e to the minus t to the n over n factorial. And if we insert this 1 into a series and swap the sum of the integral, we'll get an extra factor of n factorial, which will help the series converge. It will make make the terms in the series grow more slowly. So the Borel sum of a divergent series is defined to be the integral from 0 to infinity dt e to the minus t. We've just inserted 1 in our series and swapped the sum of the integral. And so we've got this extra factor of n factorial, which helps make this sum more convergent than just the sum of an. So this is another way we can try to assign a finite number to a divergent series. And just to note, this is a special case. At the end of the lecture, I'll briefly talk about the more general case. So there's a more general procedure we can use known as Borel summation that has an extra parameter. I've just set that extra parameter to 1 for now. Okay. So this is another way we can assign a finite number to a divergent series. And compared to Euler's summation, we've got an n factorial instead of just the power of x to the n. So so this is a more powerful technique. We don't need to put as strong of a condition on the ANs in order to have a finite Borel sum for a divergent series. Okay.
Sorry, can we guarantee that if we take a convergent series, can we get the same result as we just do the summation of the series instead of the Borel summation?
So for a convergent series, we've just inserted a factor of 1, swap the integral. So if we
Yes.
so we're allowed to change, if it's an absolutely convergent series, we're allowed to change the order. So in that case, we'll recover what we originally started with. Okay. So again, I'm going to give you a few minutes to try to compute the Borel sum of Grandy series. And let's see what we get. So previously we got a half. This is a seemingly very different method. I'll give you a couple of minutes to work that out.
I have a question. You've written d phi bracket 1. What argument does d phi take as a function?
Oh, so at the end of lecture and in tutorial, we'll study a there's a more general procedure called Borel summation that takes, instead of just a series of numbers, it takes a series where each term is a monomial. When you finish, can you give me a thumbs up? Okay, two more minutes. Okay. Can somebody walk me through their solution? Alicia?
So if you do the sum first, if you plug in the grand
Okay.
series,
So this
realize that e to the negative t, because that's the zero representation of it.
this?
That would be e to the negative t, the sum.
Yes. E to the negative t.
Yeah. So and then you just do the integration.
Okay. So do the integration. Get minus 2t is I have
I think we need a negative sign. Negative.
negative. Yes. Thank you. Good. So we get the same thing. So this is, in fact, not an accident. Euler and Borel summation always agree if both exist. And show that. So it's something we can do, and it's not as arbitrary as it seems before. We've come up with two very different summation procedures, and they both give us the same example, same answer for this example, and it can be shown more generally. They always agree. So it's not something we can make well defined, as we've seen, and it's not completely arbitrary. And in fact, many series can be summed without even specifying an explicit procedure like the ones we've done. So there's we just specify a few properties that we would like our summation procedure to have. In fact, using those properties, that's enough to sum many series. So one property that would be nice for our summation procedure to have is if we act with our summation procedure or summation machine on some series, it should give us the same thing as if we add the first term in the series to the summation machine applied to the rest of the series. So this is something that finite sums. It's a property of finite sums. And it would be nice if this is held for a more general summation procedure that works on divergent series. This is another property that we might like our summation machine to have is that if we act with our summation machine on a linear combination of two series, where alpha and beta are just constants, we'd like our summation machine to be linear. Again, that's one of the key properties of ordinary addition that we'd like to maintain. So this should give us alpha times the summation machine applied to the first series plus beta times summation machine applied to the second series. So this property is linearity. The first property is a shift property. So these two properties, are rather basic properties, we expect addition to obey, or more generalized addition. And this is enough to some Grande series. So I'll give you one more exercise. Show that using only these two properties, well, the sum of Grande series, so that's what we, by now we expect that we should get a half. And in fact, we can derive that using just these two properties. So I'll just give you, for the last time today, a couple minutes to work that out. We finished the thumbs up? Yeah, give you 2 minutes. Okay. Can somebody walk me through this one? Yes.
By the first property, the sum should equal to 1 plus s starting with -1.
Okay.
But then starting with -1 is negative of the original sum
Okay.
by the second property.
Good. This is property number 1, property number 2. So if S is the sum of the whole series, S is 1 minus S, or S is a half. So any procedure that satisfies these two very basic properties will assign the same value to this divergent series. So it's not a completely arbitrary thing to do to assign a finite number to a divergent series. There are broad classes of procedures that all give you the same answer, and we'll often do this in physics. We'll assign finite numbers to divergent series or divergent integrals, and we'll see throughout a number of examples that it won't really matter which procedure we use, as long as it's a procedure that respects some of the basic properties that we expect integrals or sums to respect. So these procedures for summing divergent series are, well, nice because they're some of the simplest ones. So they illustrate the idea. For practical purposes, these are not necessarily the ones you would want to use. So one bad property of the summation procedures I've discussed so far is that we need all of the terms in the series in order to sum the series even approximately, which is not, so in physics, in some cases we can compute all the terms in the series, but there's definitely many cases where we can't. We only perhaps can compute the first few terms in the series. We might know if the series is divergent, but there are other procedures, summation procedures, that will give the same answers for the sum of the divergent series that do have the property that the first few terms will give an approximation to the final answer. So one of the more powerful ones is called PAD-A summation, which uses rational functions to sum divergent series. Okay. Are there any questions so far?
So still not all divergent series would converge under a summation procedure like this.
That's right.
Is there a condition on like what kind of series would converge and what would not?
For this generic summation machine, I'm not sure what the general condition for this generic summation procedure to work. It's for Borel and Euler summation. It's easier to see what kinds of series will work. This one, we'll see some examples in tutorial where it works. I'll have to think about that. Okay. Other questions? Yes.
How should we view the result of such summation what does it mean for this summation to converge and what does it mean to not converge? For example, for the usual series, we know that if we take a calculator and we keep adding the terms, it will converge towards the value that we get. But in this new type of convergence, how should it be interpreted?
Well, so in a sense, so what we're in general. Comes out of me. So in a sense, what we're doing is we're generalizing the ordinary procedure. So both of these procedures will give the same results as just punching it into a calculator for any series that does converge. These are a more powerful technique that extends the types of series that we can sum. And just like the sum of a convergent series gives you some information about a series, these sums of divergent series contain some information about the original series. So I'll have more to say about that in the case of a perturbation series, and that's the next thing I'm going to talk about. But this number of a half is like it contains information about Grandy series. That's if you had to write down a finite answer for Grandy series, there's really only 3 numbers you could think of. It would be either a 0, 1, or a half. Even before this procedure was still understood, a half was the answer many people tried to justify with various less rigorous methods.
Is there a proof for why they both agree? Because I don't.
Yes, there is a proof. It's not one I can summarize off the top of my head, but I could give you a reference if you're interested. Other questions? So in physics, one of the most common, but definitely not the only place we run across divergent series is when we're doing perturbation theory. And what we'll commonly get as a result of our calculation is an asymptotic and divergent series in some small parameter, which I'll call G. So this F is some exact quantity of interest. And usually the best we can do is get a divergent series. So a natural question to ask is how can we get back to F if we only have this divergent series, I'll call phi G. And so how to go backwards? This way we can do it through perturbation theory. And often, sometimes we can go backwards via a summation procedure like this. And we'll see an example of that in tutorial where we can do that explicitly. We'll first construct an asymptotic series. I'm just in a simple example, and we can go backwards. So And I'll say a bit more about that in a few minutes. But first, I wanted to give a physical argument, originally due to Dyson, for why we expect that many of the perturbation series we construct in physics are divergent. So Dyson's argument, which I will slightly adapt into a slightly different context than his original argument, but it's the same basic idea. Apply his argument to a quantum mechanical particle with a potential V of Q is Q squared plus G Q to the fourth. So Q is here some position and G is a parameter. And let's suppose the quantity we're interested in calculating, our exact quantity of interest, is the ground state energy. So if G is positive, then V of Q just has some global minimum near Q equals 0. The ground state energy we expect is real, some number we could calculate. And in particular, the imaginary part of the ground state energy should be 0. On the other hand, if we just change our parameter G from positive to negative, the potential looks something like this. And the minimum at the origin goes from being a global minimum to just a local minimum. And this potential is unbounded from below. So it doesn't have a real ground state energy. It does have a resonant energy. So we can interpret for an unstable potential instead of the ground state energy doesn't exist, but we can a closely related thing is the resonant energy, which will have an imaginary part. So the resonant energy would be something like the energy of a state that's localized near this metastable minimum, and it would have an imaginary part because of time evolution. Through time evolution, the particle will tunnel through here, and it's not a there's no eigenstate of the Hamiltonian that remains localized near the origin for all time. So there'll be an imaginary part. So we've got a situation in which quantity of interest for any value of G that's positive has 0 imaginary part, and it has a non-zero imaginary part for any negative G. And so if we construct a series approximation to the ground state energy, it has to have 0 radius of convergence. If it had a finite radius of convergence, then for G around G equals 0, then there's no way that the imaginary part could abruptly change from being 0 in an entire region to being non-zero. So there's no analytic function with that property. So E of G a series approximation, so it's phi of G must have 0 radius of convergence. And this is if we think about why this is the case, there's an interesting connection here between the perturbative physics when G is positive. So if G is positive, we might want to compute the ground state energy just as a perturbation series in G. But the fact that we can't get a convergent series for doing that is connected to the fact that if G is negative, this particle wants to tunnel through this barrier, which is a non-perturbative process. So there's a connection here between perturbative and non-perturbative physics. And in some cases, this can be made quantitative. So the fact that this series diverges is related to the large the behavior of the terms in the perturbation series for large n. So the coefficients of g to the n for n large determine whether or not this series converges or diverges. And so the large n behavior of the perturbative series is connected to the non-perturbative physics for G negative. So that's an interesting connection. Are there any questions about that?
Yeah, I didn't get much of it. The imaginary part, the non-imaginary part. What was that?
So this is just saying that the ground state energy should be real if we have a potential that's bounded from below. If the potential is not bounded from below, well, so we wanted to time evolve a state that was localized near where the minimum was. So if we just looked at perturbation theory, we could say that we wouldn't know about this part of the potential. We could calculate some approximate ground state energy for just by doing perturbation theory around this metastable minimum. So that would give us some real answer if we just ignored what's going on over here. Included this part, that would give us a correction to the ground state energy that has to have an imaginary part because the particle is not going to remain localized through here. Eventually it's going to tunnel out and the wave function will spread. Or in other words, so if we have a particle in the ground state, the probability of it remaining in the ground state will be 1. So that won't be true if we have a particle that's in the would-be ground state, or approximate ground state, the resonant state. That's the state that would be what the ground state energy would be if we ignored this part of the potential. So the probability of the particle remaining there should not be 1 for all time. It should have some probability of decaying. And if we give the one way of saying that the probability that the particle will remain in that state won't be 1 for all time is to give the energy an imaginary part, so that the time evolution will be e to the I e naught t. If this has an imaginary part, this is no longer a just a phase. It will have an amplitude that decreases. So that's why I claim that.
Okay, and how is that related to the zero radius of convergence?
So if it converged, if at g equals 0, the series expansion for the ground state energy converged, it had a finite rate of convergence. It would have to work for both g positive and negative. So there have to be some analytic function in a neighborhood of g equals 0 that was identically had a 0 imaginary part. So So if we looked at the real part of G, imaginary part of G, so some finite radius of convergence. So over here, the imaginary part is 0. So, and over here, the imaginary part is non-zero. There's no analytic function like that. So we wouldn't have a finite radius of convergence. Analytic functions that are identically 0 or have an imaginary part that's identically 0 in some region should have that everywhere. So this doesn't work. Okay. So I want to say a few words about how we can go back approximately first. So typically, in both quantum mechanics and in QFT, coefficients for large N grow like some constant, the minus n times n factorial. And so what we get if we just consider, we plot the partial sum of n terms, and is indicating how many terms we take in the partial sum, versus the error between the function we're interested in and the partial sum. What it'll typically look like is our approximation will get better and better, and then get worse and worse. Because our series diverges, the thing we're interested in computing, it's finite, so if we take too many terms, eventually our approximation will get better, and there's some optimal place at which adding more terms for fixed value of G just makes our approximation worse and worse. And it's typical that the optimal truncation is to keep up to the smallest term in the series, which, if the coefficients grow like this, means that the n star minimizes an g to the n, and so that's some constant times n factorial for g over a. A is another constant to the n, which is c times the exponential of using our approximation for n factorial from last week, n log n minus 1 minus log of A over G. And for large N, this is minimized when N is about A over G. And then the error is typically like the next term. So the error will be like E to the minus A over G. So it's exponentially small, which is generally way better than you can do with a convergent series. So even though the series doesn't diverge, doesn't converge, it's generally for a finite number of terms a much better approximation than a convergent series. So this exponential accuracy is very good. And so it's, if we're interested in comparing to experiment, it's generally much better to have a divergent series than a convergent series. And another thing to notice is that this error, the best you can do with a divergent series, at least using this simple technique of just truncating after a finite number of terms, is so this the irreducible error that you can't get rid of is some non-perturbative function. So you remember from before, there's a non-perturbative functions are invisible to asymptotic series. So that's something we could never see a term like this in an asymptotic series, and the error is typically some non-perturbative function. So again, there's this connection between the perturbative series and the non-perturbative series. And you may have noticed that I said typically a lot in this part of the discussion. You can construct asymptotic series that have different behavior. This is often the case you get, but you can't show that. You need to put additional restrictions on your function or A to show that this is always the case. Are there any questions on optimal truncation? Okay. So I just want to return to the Borel summation from before and briefly explain how to do Borel summation in the case where we've got a series like a series that depends on a parameter. So in the case that we have a series like that, we can define the Borel transform of the series as the sum of n over n factorial, en factorial. And the Borel sum, in the general case, is the integral of e to the minus t of phi hat of zt, which is just the same as what we had before. Before I said z equal to 1. And so this more general procedure is useful because sometimes it lets us go back from the asymptotic series to recover the exact quantity of interest. So one nice property, so we can rewrite this as e to the minus t times the sum of an over n factorial z to the n t to the n dt. And this has the property that it recovers the same asymptotic series. If we apply this to some asymptotic series, the Borel sum has the same asymptotic series. So if we just swap the sum and the integral, we can get the asymptotic series. We'll get the sum n equals 0 to infinity an over n factorial. Then the integral is just the integral of e to the minus t gamma to the t, which is gamma of n plus 1 z to the n, which is just our original asymptotic series. So that's a nice property of the Borel sum. It has the same asymptotic behavior as the divergent series. We can use the sum with it. And one nice and so that means that it's a good candidate for going backwards. So sometimes we can go backwards, and from a asymptotic series that we construct using perturbation theory, sometimes it's possible to reconstruct the original quantity of interest, something like ground state energy. So this is sometimes, and sometimes we need additional information about the non-perturbative aspects of this function. So things like how, if we're interested in ground state energy, we might need some information about the tunneling when the parameter is negative. So and that this non-perturbative information can show up as an obstruction to doing this integral. So sometimes this Borel transform can have a singularity or can be non-integrable on the real line. And so we need to know, and the non-perturbative information about f can lead to singularities of the Borel transform on the real line. So this is something that can be done in some cases. It's not fully understood, but it's we'll see an example in tutorial where there's just a simple example where we can construct a asymptotic series solution to a differential equation that diverges, and then we can go backwards and actually construct an exact solution using Borel summation. It's kind of cool. So, are there?
What do you mean by phi z? Phi z is it a definition of phi z?
So it's just the original
Yes.
series with, I changed the argument. It's a function of a different variable. I could call this g if I liked.
What do you mean by that we might need non-perturbative info? What kind of non-perturbative information would you?
So the asymptotic series, if we have an asymptotic series of this form, and the function over here contained a contribution that was like e to the minus 1 over g squared, this asymptotic series would not contain any information about that term in f. So we might need to supplement the asymptotic series with some information about what kinds of non-perturbative functions are contained in f. Any other questions? Okay, so we've covered a number of different topics in this course: distributions, asymptotic series, and how to sum divergent series. And I look forward to seeing how to apply these into quantum field theory with you in the quantum field theory 1 and 2 courses in a few months. So thank you for your attention.